Okay, good. Okay, so echelon means stairs or staircase. Okay, so can we just bring our that matrix? What is it? We have just written that augmented matrix. It is something like this, right? And here we have a bunch of numbers here, the entries of A, and also here we have column vector. By doing some kind of operation, all right, can we just bring this into this form? That means that here, what actually this stairs stand for? Here we have the first variable. If you're talking about, let's say, uh, um, a system of equations with n variables. So maybe here we have x sub 1, and here we have x sub 2, and here we have x sub 3, here we have x4, x5, continuous. Under this, here we have zeros, right? As see here, maybe let's say we are talking about a system of linear equations with 5 equations. As see here in the last line, we have only one term, right? It contains only one variable. That means that just simply it is like this equation, ax equals b. And we know how to solve this. Find x5 here, and using this one, substitute here, and also here we may have x5 here, we may have x4 and x5, blah, blah, blah. By back substitution method, we can get the values of all of these variables. So now, row echelon form. When do we say that a given matrix is in a row echelon form? So a matrix is in row echelon form if it satisfies the following properties. And we have two properties. The first one is any rows consisting entirely of zeros are at the bottom. That means that if you have any row, all entries are 0, we should actually put them at the bottom part of the matrix. And second one is in each non-zero row. Each non-zero row, what does it mean? It means that at least here we have a kind of row, right? Row matrix. Maybe here we have 0, 0, 0, 2, 0, 0. It may be different way. Here we have maybe 0, 1, 2, 3, 5, 6, 7. Maybe here may be 1, 2, 0, 3, 2, 1, something like this, whatever it is. That means that in each non-zero row means at least one entry is non-zero. That's not equal to 0, right? The first non-zero entry called the leading entry, right? The first non-zero entry here, for example, what is the first non-zero entry? It is 2, right? And here, what is the first non-zero entry? It is 1. And let me just write here 7. And what is the first non-zero entry here? It is 7. Right? We mean this. So we call them leading entry. Leading entry means the first non-zero entry is in a column to the left of any leading entries below it. Right? For example, if I'm putting here, see here, this is a leading, right? So it should be to the left of any leading entry below it. So this must be, if I have to put in that order, this should be at the top. And in the second line, this will be in the first line, right? This must be in the second line, and this should be in the third line. Then it becomes in row echelon form. Now, for example, the following matrices are in row echelon form. As you see here, 2, 4, 1. The first leading entry here is 2, right? And in the second line, it is -1. As you see here, this column, right, the first column is to the left of the second one, because here the leading entry comes after 2, right, in the second place. And how about here? All entries are 0. That's why we place this row at the bottom. So now this matrix is in row echelon form. And how about the second one? The first leading entry is, here we have 1, right? And the second line, the first leading entry is 1. In the third row, the first leading entry is 4, right? And the definition, as you see here, in each non-zero row, right? The first non-zero entry, called the leading entry, is in a column to the left of any leading entry below it. So you see here below this, right? To the left, right? Here also to the left. For example, this one is to the left of this. This one is to the left of this leading entry below this. The same way also, this matrix is in row echelon form. This is the leading entry, and all actually, as you see here, after under leading entry, all entries are 0. In the second line, this is the leading entry. All entries are 0. And here we have 0 row that is at the bottom of this matrix. In a similar way, here the leading entry is 2, right? And the next one is -1. As see here, leading entry, all entries under this leading entry, this 0. Leading entry, all are 0. And here we have leading entry 4, and that is 5. As see here, it looks like a stair, right? From here, and row here, and row here. That's why it is called in row echelon form. How about here, something like this? And how about here, it is something like this, right? How about here, it is something like this. So the pattern looks like a state. That's why it's called low echelon form. Assuming that in example 2, each of the matrices in example 1 is an augmented matrix. Augmented matrix is, what is it? The constant term, right? The constant matrix. I mean, the vector, column vector, is added or augmented to the coefficient matrix. Write out the corresponding systems of linear equations and solve them. And solving part, let's just, let's say this one is, let me change my color. Let's say that one is the first one, that is the second one, and third one, and fourth one. We're not going to do all of them. Let's just write the first one. Okay. Here, first, it says that write out, right? The first part says that write out the corresponding systems of linear equations. So we have only from here, how many variables we have here? Here we have 2 variables. Well, why? Because we have 2 columns here. So I can use only x and y. So here that's the coefficient of x. So here we have 2x plus 4y. That's equal to 1. And the next one, 0 times x. So it's just x. So here we have minus y is equal to 2. And the last line is all zeros. So we don't have to write this. How about the second one? The second equation, the second matrix is 1, 2. So here we have 2 columns. That means that this system has 2 variables or 2 unknowns. So here we have 1, that is x. And here we have 0. 0 times y is 0. So here we have 1. In the second line, here we have 0 times x plus 1 times y. So here we have y is equal to 5. In the third line, here we have actual non-zero elements. That's why we need to write this. Here we have 0 times x plus 0 times y. So here we have, what is it? 0 is equal to 4. So that is our system. And how about the third one? As see here in the third matrix, augmented matrix, we have, what is it? 4 columns. So that means that here we have 3 variables because the last one is constants. What is it? The column vector of constant terms, right? That's the column vector with constant terms. That represents actually the constant terms in the system. So here, x times 0, that is 0. Sorry, so we talked about 3. So 1 times x, that is x, plus 1 times y, that is y, plus 2 times z, that is 2z, is equal to, here we have 1. And here we have 0 times x plus 0 times y, that's 0. And here we have only z. So z is equal to 3. The third line also zeros, right? So we don't have to write anything. It's just equal to 0 equals 0. And how about the last one? The last one is 1, 2, 3, 4, 5, excluding the last column. So here we have 5 columns, right? And that the last one is just the augmented column. So that means that here we have 5 variables. If we have variables, I mean more than 3, we better use subscript notation. So here we will have 0 times x1, nothing. And here we have 2 times x2 plus 0 times x3 plus 1 times x4. And here we have minus x5. That's equal to 3, right? And how about the second line? 0 times x1, 0 times x2, negative 1 times x3, that is minus x3, plus x4, plus 2x5, that is equal to 2. And here we have 0, 0, 0, 0. So the last one is x5. So x5 is equal to 0. And the last one is 0. On the right-hand side, we have non-zero number. That's why we need to write this equation. 0 equals 5. So that is the system of linear equations, which is represented by this augmented matrix. Okay. Next. Now we will introduce another important keyword. That's a keyword of this chapter. Or is it elementary row operations? And actually you have seen this in the first slide, right, in keywords part. What do we mean by elementary row operations? The following elementary row operations can be performed on a matrix. So actually, when we just say elementary row operations, we mean the following operation. Number one is interchange two rows, right? So if you're given two equations, like immediately, let's say, just example, let's say we are given this kind of system, 3x plus 5y is equal to 7, and 2x minus y is equal to 6, for example. And it is augmented matrix, right? Or any matrix, let's say augmented matrix, coefficient matrix, doesn't matter. Our augmented matrix will be this, that is A, vertical line, here we have B. What is it? Here we have 3, 5, and 7. Here we have 2, -1, 6. All right. So it's saying that basically, if you just interchange two rows, right, and that is called elementary operations, and also in solving system, it does not change the solution of the system. That's why we can do this operation on the matrix. That means that I can just write this equation like this, right? 2x minus y equals 6, and 3x plus 5y is equal to 7. I just interchange this, what is it? These equations. Then what will be the augmented matrix of this one? Let's say this B, B. So this will be, here we have 2, -1, 6, 3, 5, 7. So if you just interchange these two rows, it does not affect the solution of this system. So multiply a row by a non-zero constant. And also, as you know, that if you just multiply any row of the matrix by a constant number, we call this elementary row operation. It's something like this, multiplying, let's say, both sides by 3, and multiplying both sides by 3. Again, it does not change the solution of this equation or system, right? That is another elementary row operation that we use to solve this system of linear equations. And it says that add a multiple of a row to another. And usually this operation, when do we use this? To eliminate the variables, right? Here, for example, if I want to eliminate x here, how can I eliminate this? Or let's say y here. I should multiply the first row by 1/5, right? And 1/5 times 5, it will be y. And I should add it to the second equation. Then y plus -y will be equal to 0. So y will be gone. So I will have only x. So adding a multiple of a row to another one. How actually we denote this by, using mathematical symbols. Interchanging two rows means it is this. Interchanging this one as row I, right? And here we have row J. I'm interchanging I to J and placing J to I's row. And how about this one? Multiply a row by a non-zero constant. That means that multiplying a row, any row, let's say row I, by a constant. Here, k is not equal to 0. Because if you multiply by 0, everything will be disappear, so we don't need that. And the last one is add a multiple of a row to another one. That means how do you do that? So multiplying, add a multiple of a row to another one is, that is k times RA, and we are adding to the J's row and writing this in J's row. Okay, that is how we represent mathematically. Using symbols. All right, so elementary operations: interchange two rows, multiply a row by a non-zero constant, add a multiple of a row to another one. All right, reduce the following matrices to echelon form. And to do this one, actually, we need to use elementary row operations, because we use elementary row operations to reduce the matrix to maybe echelon form, or soon we will see that the more powerful one, reduced echelon form of a matrix. Okay. All right. To do this one first, let's start with the first one. Okay. Here we have 3, 2, 1, 4, right? And since it is 1, I can just interchange this, so it is easy to eliminate this 3. That is 1, 4, 3, 2. What did I do here? I just interchanged the first row, right? Interchange the first row with the second row, right? First and second row interchange here. And now, how can I eliminate, for example, create zeros under 1? Because that is a leading entry, right? 1, 4. To eliminate or to create zeros under this leading entry 1, I should multiply the first row by -3 and add to the second line or second row. So multiply by -3, -3 times 1 is -3 plus 3 is equal to 0. -3 times 4, -12 plus 2, that is -10. As see here now, it is in row echelon form. And how about the second one? Here we have 3, -2. Let me just write the matrix first. Let me just write everything here. 3, -2, and -1, and 2, -1, -1, and 4, -3, -1. Right? All right. To do this one, what we have to do here is, okay, actually I can just do like this from here, or I can interchange it so it is easy to eliminate these things. Okay, no problem. The first one is, let me create 0 here in the third line, third row. To do this one, I will multiply the second row by -2 and add to the last row. So here we have 2, -1, -1, multiply by -2 and add 4, that is 0. -2 times -1, it is 2, plus -3, it is -1. And -2 times -1, it is 2, 2 plus -1, it is 1. Okay, so now we created 1, 0 under this. Second one is, how can I change this 2 into 0? To do this one, I should multiply this 3 by, what is it? 2 over 3. So I will multiply, basically what we are doing here is, I will multiply, okay, the first row of the matrix by -2 over 3, and we will add this to the second row. So here, let me just write the first row, 3, -2, -1, and if you just multiply here, 3 by -2 over 3, that's equal to -2, and add it to this 2, here we have 0. Okay, here we have 0. Now, I should multiply -2 over 3, right? Let me just do this calculation here. -2 over 3 times, this one is -2, and I should add this to -1, so that is -1. That's equal to, here we have 4 over 3 minus 1, which is equal to 1 over 3. So this entry is 1 over 3. And the last one is multiply by -2 over 3, -2 over 3 times -1, right? And add to -1, that's -1. So 2 over 3 minus 1, which is equal to -1 over 3, -1 over 3. Now here we have still -1 and 1. Okay. And as you see here, we have 1 over 3, -1 over 3. Another elementary row operation, let me multiply the second row by non-zero constant, right? We can do that. That's the second one, right? So here we have 3, -2, -1. Why am I doing it here? This operation, applying this operation to this, because here we have fraction. I just want to convert them into whole numbers or integers. So multiply the second line by 3. So here we have 0. 3 times 1 over 3, that is 1. And 3 times -1 over 3, that's -1. And here we have 0, -1, and 1. And if you just multiply the second row by 1 and add to the last line, the last row, what we have here, -3, -2, and -1. And here we have 0, 1, negative 1, and 0, 1 plus negative 1, 0, negative 1 plus 1 is 0. So here we have 0, 0. Now it's already in echelon form, right? And this 3 and this 2, these are leading entries of this matrix. Okay. So in a similar way, you can do the last one. I will skip this for you. Okay. Another one is, so far now actually you have become familiar with, what is it? Constant coefficient matrix, augmented matrix, right? And echelon form. And now after that, what did we just learn? What is it? Elementary row operations, right? And now we have another keyword here that is row equivalence. Okay, when we just say that two matrices are row equivalent to each other, if there is a sequence of elementary row operations that converts A into B by applying a bunch of elementary row operations, if I actually convert this A into B, okay, then we say that these two matrices are row equivalent to each other. And what are those elementary row operations? We have just studied that thing, right? Either interchanging two rows or multiplying a row by a non-zero constant number, or multiplying a row by a constant number and add it to another row. That is just using these three operations, okay? A bunch of these operations, can we just convert A into B, for example? So if we can do so, then actually these two matrices are, what is this, elementary, row equivalent to each other. All right. So for this matrix in A, for example, so can we just, using some elementary row operations, can we convert this into this matrix B, for example, here, right? To do this one, we should start from here. Let's say matrix A. That matrix A, that is equal to what we have here, 1, 2, 3, 9. And here we have 2, negative 1, 1, 8. And 0, 3, 0, negative 1. Here we have 3, right? The first one. Here, as you see here, 1, 2, 3, 9, 1, 2, 3, 9. The first row is the same. So we don't have to do anything with the first row. Now, under this one, here we have zeros. First, let's just create zeros under one. To do this one, let me just write the first row here, 1, 2, 3, 9. How can I get 0 here under 1? I need to multiply the first row by negative 2, right? So I should do this operation, multiply the first row by negative 2 and add it to the second row. If you do so, negative 2 times 1, negative 2 plus 2, that's equal to 0. Negative 2 times 2, negative 4 plus negative 1, that is negative 5. Negative 2 times 3, negative 6 plus 1, negative 5. Negative 2 times 9, negative 18 plus 8, that is minus 10. And here we have 3, right? And to have 0 here, let me multiply the first row by negative 1 and add it to the third row. Now what we have here then? So minus 3 times 1, it is minus 3 plus 3, that's equal to 0. Minus 3 times 2, it is minus 6. Minus 6 plus 0, that is minus 6. And minus 3 times 3, it is negative 9 plus negative 1, it is negative 10. Negative 3 times 9, negative 27 plus 3, negative 24. Continue. And 1, 2, 3, 9, the second line, right? As you see here, all numbers, all entries are divisible by negative 5. Let's multiply. The third operation is multiply the second row by minus 1 over 2. What do we have here then? Here we have 0, and here we have 1, here we have 1, here we have 2. Now we obtain the second line. And how about here? All numbers are divisible by negative 2. Let's do that. That is, what is that? Minus 1 over 2 times R3. So here we have 0. Negative half times negative 6, that is 1 over 3. Sorry, it's just 3. And this 3. And here we have 5. And here we have 12. Okay. So 1, 1, 2, also the second row the same. That's good. Continue. 1, 2, 3, 9. The second line is 0, 1, 1, 2. And the last row is, actually, it's always 0. Multiply this third row. That means that multiply the second row by negative 2 and add it to the third row. What do we have here? Negative 3 plus 3. 0. Negative 3 plus 5. Right? That's equal to 2. Negative 6 plus 12. That's equal to 6. Now, the last one is, if you multiply 1, 2, 3 is 9, 0, 1, 1, 2. If you multiply the last row by 1 over 2, we will get 0, 0, 1, 3. As see here, and I just did here, multiply the last row. Actually, it's a minus. So that is 1 over 2 R3, right? We just multiply the last row by 1 over 2. That's our last elementary row operation, and we obtain this. As you see here, that is exactly the matrix B. So by applying a bunch of elementary row operations, we have converted matrix A into matrix B. That means that these matrices A and B are, row equivalent. So these two matrices are row equivalent to each other. Okay. In similar way, you can practice this question, matrix A and matrix B, and can you just convert A into B or B into A? From here, as you see, converting A into B is much easier because B is already in row echelon form, right? And after that, we can decide either these two things are row equivalent to each other or not. Okay, now we have important theorem here. So matrices A and B are row equivalent if and only if they can be reduced to the same row echelon form. And here we are saying that if and only if, the mathematical symbol for that is this. If and only if, or sometimes we just write IFF. That means that if and only if. What does it mean? It means that matrices A and B are row equivalent, then they can be reduced to the same echelon form. Or two matrices A and B, if we can reduce them to the same echelon form, then A and B are equivalent. So we have two-way implications here. That's why we are using here if and only if. It means that actually if one is true, another one is true. If another one is true, the first one must be true. Okay. Gaussian elimination. Now, actually, maybe the first time Gauss actually used this method or published this method in a paper. That's why it is credited to his name. And how do we actually solve a system of linear equations by Gaussian elimination? To do this one, first we have to write the augmented matrix of the system of linear equations. As you know that in the previous example, the first one assumed that we need to solve this equation. Let's say 2x plus 2x plus 3y equals 4. Let's say here we have 3x plus 5y is equal to 7, right? And the first step, it says that write the augmented matrix of the system of linear equations. So what is the augmented matrix for the system? That is this matrix, right? It is 2, 3, 4. And the last one is the, the column of constant terms. So here we have 3 and 5 and 7. In the second step, use elementary row operations to reduce the augmented matrix to row echelon form. So in the second step, let's say this one is, let's say matrix A. So we have to change this matrix A into B, where this B is in echelon form. That means that we have some kind of staircase like this, right? And using back substitution, starting from the bottom, right? Using back substitution, solve the equivalent system that corresponds to the row reduced matrix. So now, once we actually wrote this in the row echelon form, starting from the last variable, right, we can find the value of y here. Then starting in the first line, you can find the value of x. Okay, and solving system of linear equations using this method is called Gaussian elimination. Let's see one example for this. Solve the system. Here it means to solve the system using the Gaussian elimination. And the first step we have to write it is augmented matrix, right? So the augmented matrix is, here we have 1 and 3, -2. Here we have 3, -2, 5. The second line is 3, 5, 6, and 7. Third one is, it is 2, 4, 3, and 8. All right. So by Gaussian elimination, the first thing is, right, we need to write the augmented matrix. Now we have to reduce this to row echelon form. I don't know how to do that. So here we have, let me just write the first row, 1, 3, -2, 5. And I need to create zeros under 1, right? To do this one, multiply, the first one is multiply the first row by -3 and add it to the second row. So -3 plus 3, I mean -3 times 1, it is -3 plus 3, that's equal to 0. -3 times 3, it is -9 plus 5, that is -4. -3 times -2, it is 6. 6 plus 6, that is 12. -3 times 5, -15 plus 7, -8. And how about here for the third row? I should multiply the first row by -2 and add it to the third row, right? So then we will have here -2 times 1, -2 plus 2, that's equal to 0. -2 times 3, -6 plus 4, -2. -2 times -2, 4. 4 plus 3, it is 7. -2 times 5, -10 plus 8, that is -2. Okay. Next thing is 1, 3, -2, 5. Okay. I can simplify the second row, right? I can just divide by even 4. If you divide by -4, what we have here? 0. -4 is divided by -4. It is 1. Here we have -4. So it is -3. -8 divided by -4. That is 2. And here we have 0, -2, 7, -2. Now that one is pivots. Actually, it doesn't have to be 1, but I just did this to get simpler form. And now I need to also create 0 under 1. So to do this one, 1, 3, -2, 5. And here we have 0, 1, -3, 2, right? And 0, I should multiply the second row by 2 and add it to the last row. That's equal to 0. 2 times -3 plus 7, that's equal to 1. And here we have 2 times 2, 4 plus -2, that's equal to 2. Now it is already in row echelon form, right? The second step is done. So now using back substitution, we have to solve this. And what we have here, now if we just rewrite this, here we have x plus 3y minus 2z is equal to 5. In the second row, here we have y minus 3z is equal to 2. And the last one is z is equal to 2. Now, using this and applies to the second equation, what we have here? Y, let me just continue here. Y is equal to 2 plus 3 times z. Z equals 2, so that is 6, so that's equal to 8. Now we know the value of y. The last line, x is equal to 5 minus 3 times y. Y is equal to 8 plus 2 times z. Z equals 2, which is equal to 5, it is minus 24, plus 4 is minus 20, that's equal to minus 15. So dot, 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 I can write the solution of the system as x, y, z as a vector. What is the solution? The solution is -15 and 8 and 2. That is the solution of this system. Okay, guys, let me stop here. Okay, 15 minutes break. What time is it now? It is 10:46. So we will continue our class at 11 o'clock. Okay, we have around 1 minute left. I want to finish here. And next we have one more example and I will finish the class. Okay, good. Okay, enjoy your break. See you after 15 minutes.
See you, sir.
See you.